Right now, at the center of our galaxy, there's a monster with a gravitational pull so extreme that even light can't escape. If you fell into it, something impossible would happen. You'd experience the end of your life in seconds, while the universe outside aged trillions of years. Black holes aren't just cosmic vacuum cleaners. They're places where the rules of space and time completely break down. And if you actually fell into one, the experience would be so strange, so counterintuitive, that even Einstein struggled to accept what his own equations predicted. This isn't science fiction. This is what general relativity tells us would really happen to your body, your perception, and your place in time. So let's take that fall. Let's go through the event horizon, and let's see what happens when you reach the point of no return. First, we need to understand what a black hole actually is. It's not a thing. It's a region of space-time. When a massive star collapses, it compresses so much mass into such a small space that it warps space-time into a cosmic trap. The boundary of that trap is called the event horizon. Cross it, and every possible path you can take leads inward to the singularity. Outside the event horizon, physics works normally. Light can escape, matter can orbit. You could turn your rocket around and fly away. But the moment you cross that invisible boundary, the geometry of space-time itself changes. Future and inward become the same direction. Think of it like a waterfall. Above the falls, you can swim in any direction. But once you go over the edge, there's only one way to go. The event horizon isn't a physical surface. There's no wall, no barrier, no sudden change you can feel as you cross it. For a supermassive black hole like Sagittarius A star at our galaxy's center, the event horizon is 17 million miles across. Here's the wild part. The tidal forces at the event horizon of a supermassive black hole are actually gentle. You wouldn't feel anything unusual crossing it. But for a stellar mass black hole, just a few times heavier than our sun, the event horizon is only a few miles wide. The smaller the black hole, the more extreme the tidal forces become near the event horizon. And that's where spaghettification begins. Tidal forces happen because gravity gets stronger the closer you get. Your feet are closer to the black hole than your head. For a small black hole, that difference in gravitational pull between your head and feet becomes enormous, lethal. Stretching. The technical term is tidal disruption, but physicists call it spaghettification. And that name is disturbingly accurate. Italian astrophysicist Andrea Ghez spent decades tracking stars orbiting our galaxy's central black hole to prove these monsters really exist. She watched one star complete a full orbit in just 16 years, reaching speeds of 5,000 miles per second. The math was undeniable. In 2020, she won the Nobel Prize for proving that Sagittarius A star is real. 4 million solar masses compressed into a region smaller than Mercury's orbit. So let's set up the scenario. You're in a spacecraft approaching a stellar mass black hole 10 times the mass of our sun. Your ship is equipped with a powerful radio transmitter. Every second, you broadcast a signal back to your friend who's safely watching from far away. As you get closer, you notice something strange. The black hole doesn't look black. It's surrounded by a super hot accretion disk glowing blue-white. That disk is matter spiraling inward at incredible speeds, heating to millions of degrees through friction before it crosses the event horizon. You also see something impossible. The black hole is surrounded by a bright ring of light that seems to wrap around empty space. That's gravitational lensing. The black hole's gravity is so strong, it bends the path of light from stars behind it, creating a distorted halo. You check your instruments. You're still 50 miles from the event horizon. Gravity here is strong, but manageable. Your engines could still escape, but you're committed to the experiment. You shut down the engines and let gravity take over. The fall begins. At first, nothing feels different. You're in free fall, weightless, just like an astronaut in orbit. No sensation of movement at all. But your friend watching from far away sees something different. Your ship's radio signals are arriving slower and slower. Time dilation has begun. The stronger the gravity you experience, the slower your clock runs compared to clocks far away. When you're 25 miles from the event horizon, your friend receives one signal every 2 seconds instead of every second. You don't notice anything wrong. Your watch still ticks normally. You're still broadcasting once per second by your own clock. But from your friend's perspective, time itself is slowing down for you. This isn't an illusion. It's the geometry of space-time near the black hole. 10 miles out, the signals are now arriving every 10 seconds. The gravitational redshift is making your radio waves stretch into lower frequencies. 5 miles. Every minute that passes for you seems like an hour to your friend. The universe outside is speeding up from your perspective. You look out the window and see something astounding. The stars behind you are blue-shifted, compressed into a bright ring. The stars ahead of you seem to shift and distort, pulled by the black hole's gravity into strange arcs and multiple images. 2 miles from the event horizon. Now the tidal forces are becoming noticeable. You feel a slight stretching sensation in your body. The difference in gravity between your head and feet is no longer negligible. It's pulling you apart with a force of several Gs. 1 mile out. The stretching is intensifying. Your bones are creaking under the strain. This is the beginning of spaghettification. Your friend, watching from safety, sees your last radio signal arrive stretched and faint. Then, nothing. You've crossed the event horizon. But here's the paradox. From your perspective, you didn't notice crossing anything. There was no boundary, no transition, no point of no return. The event horizon is only meaningful to outside observers. For you, falling inward, space-time is smooth and continuous through the crossing. This is one of the strangest predictions of general relativity. The event horizon exists for everyone else, but not for you. 1 second after crossing the event horizon by your clock, the tidal forces are now unbearable. Your body is stretching like taffy. The gravitational difference between your head and feet is now hundreds of Gs. Your spine extends. Your atoms are being pulled apart. 2 seconds after crossing, you're no longer recognizable as human. You've become a stream of atoms stretched into a thin line kilometers long, but you're still conscious for these final moments. Your brain, compressed and elongated, still processes signals for a fraction of a second longer. The view around you has changed completely. The outside universe appears in a bright ring directly above you, blue shifted to extreme ultraviolet. The rest of the sky is absolute blackness. You're now inside the event horizon, cut off from the outside universe forever. 3 seconds after crossing, the singularity is approaching at near light speed. Your atomic stream is being pulled into a point of infinite density, and then, at the singularity itself, physics breaks down. Our equations give infinity. We don't know what happens there. General relativity predicts infinite curvature. Quantum mechanics says something must happen, but we have no theory that combines both. From your friend's perspective, something even stranger happens. They never see you cross the event horizon at all. The last image they see is your ship frozen in time, getting dimmer and redder, asymptotically approaching the event horizon forever. Because of time dilation, the light from the moment you cross takes infinite time to reach outside observers. You appear frozen. If your friend waited trillions of years, they'd still see you hovering just outside the event horizon, red shifted into invisibility. But you experience the crossing, the spaghettification, and the end within seconds. Two contradictory realities, both true. This is the central mystery of black holes. Two observers experience fundamentally different versions of the same event, and both are correct. Stephen Hawking spent years trying to resolve this paradox. He called it the black hole information paradox. According to quantum mechanics, information can't be destroyed. But anything that falls into a black hole seems to disappear from the universe forever. In 1974, Hawking discovered something shocking. Black holes aren't completely black. They emit radiation. Hawking radiation comes from quantum effects at the event horizon. Virtual particle pairs pop into existence, and one particle escapes while the other falls in. This means black holes slowly evaporate over time. A stellar mass black hole would take 10 to the 67 years to evaporate completely. But here's the problem. Hawking radiation appears to be random thermal radiation. It doesn't carry information about what fell in. So if you fall into a black hole and the black hole eventually evaporates, where does the information about your atoms go? This paradox has driven theoretical physics for 50 years. Some scientists think information is encoded in the Hawking radiation in ways we don't understand. Others propose that information is preserved at the event horizon itself, in what they call a holographic boundary. The holographic principle suggests that everything inside a black hole is encoded on its two-dimensional event horizon surface. It's like a three-dimensional scene encoded in a two-dimensional hologram. All the information is preserved, just in a different form. Recent work by physicists like Juan Maldacena suggests that black hole interiors might be connected through quantum entanglement to their Hawking radiation. This would mean that the information is never truly lost. It's just scrambled in such a complicated way that it seems lost. But we still don't have a complete theory of quantum gravity that fully resolves the paradox. That's the frontier of modern physics. And there's another mystery. What really happens at the singularity? Does infinite density actually exist, or does quantum gravity prevent it? Some theories suggest that at the Planck scale, smaller than 10 to the minus 35 meters, space-time itself becomes grainy and discrete. If that's true, then the singularity might be replaced by a quantum foam of space-time, preventing true infinite density. So would you really die from spaghettification? For a small black hole, absolutely. Within seconds of approaching the event horizon. But for a supermassive black hole like Sagittarius A star, you could cross the event horizon completely intact, still alive. The tidal forces at the event horizon scale inversely with the black hole's mass. Bigger black holes have gentler event horizons. You could theoretically survive for hours inside a supermassive black hole before tidal forces finally pulled you apart near the singularity. During those hours, you'd witness the end of time outside. The universe would age billions of years while you fell for minutes. You'd see stars die, galaxies collide, perhaps even the heat death of the universe, all compressed into a brief light show above you. This is why black holes fascinate us. They're not just objects in space. They're windows into the nature of time itself. Right now, the Event Horizon Telescope is studying black hole event horizons in unprecedented detail, looking for quantum effects. We're also using LIGO and Virgo to detect gravitational waves from black hole mergers, testing Einstein's predictions in extreme conditions. Future missions like LISA, launching in the 2030s, will detect gravitational waves from supermassive black holes across the universe. Every black hole we study brings us closer to understanding quantum gravity, the theory that will finally unite Einstein's relativity with quantum mechanics. And maybe, just maybe, we'll discover that the singularity isn't the end. Some theories suggest it might be a doorway to another universe. White hole cosmology proposes that black hole singularities might connect to white holes in other regions of space-time or even other universes. These ideas are still speculative, but they're based on real mathematics. The Einstein-Rosen bridge, or wormhole, is a solution to Einstein's equations. Whether any of this is physically real, we don't yet know. But the universe has surprised us before. Black holes themselves were once considered fantasy. So if you fell into a black hole, you'd experience the most extreme environment in the universe. Time would stop. Space would tear you apart. And in your final moments, you'd witness something no human has ever seen. The edge of physics itself, where our equations break down and mystery begins. Would you take that journey? Would you sacrifice yourself to be the first human to cross an event horizon and report back what you see?